form of planning we're going to do is what's called regression planner. And notice this is, instead of searching forward from the start state to a goal, we're going to search backwards from a goal state, from a goal into the start. Now what's happening here is that we're not going to have a goal state in that sense. We just have a goal description, because there might be lots of states that achieve the goal, but we don't care which one it is. So we're going to search backwards from a goal description. And then the nodes in this are going to correspond to sub-goals and arcs into actions. So a sub-goal is just an assignment of value to some of the features. So here we're not going to, so all the features that we don't care about for the goal, we're not going to include in our search space. So in the search problem, the nodes are going to be sub-goals, and there's going to be an arc between G and G prime if A achieves one of the assignments in G. So A is going to be the action that occurs immediately before G, and G prime has got to be before it. And G prime is a proposition that must be true immediately before action A, so that G is true immediately after. So we can have a node G, and then there's a neighbor G prime if starting from G prime, carrying out A ends up in G. That's the way to think about that. Okay. The start node in the regression planning is the goal to be achieved. So we're going to start with the goal. And then goal in terms of the search problem is true if G is a proposition that's true of the initial state. So in some sense, we're reversing the idea of the goal that we had before. But this is not the same as searching backwards in the state space, because the nodes here only specify an assignment to some of the features. Okay, that's what the difference is here. Okay, so let's try and define it a little bit further, a little bit better. So node G can be represented as a set of assignments of values to some of the variables. So x1 equals v1 to xn is vn. And this is a set of assignments that you want to hold. So the last action, so what we're trying to do is we're trying to achieve this. So think about what's the last action that could achieve that? Well, it has to achieve one of those xi is vi for some I. And it doesn't make any other ones different, because then it couldn't be the last action. Okay. And so A is going to be one of the last actions, and the neighbor of G along arc A must contain the prerequisites of action A, because action A has to be able to be carried out, and all the elements of G that were not achieved by A. And the other thing about the neighbor is that it must be consistent. Okay, it must have at most one value for each feature. So all the time here, all the nodes here we're talking about have to be consistent. And so let's formalize that using our strips notation we saw before. So I'm just going to rewrite what we did just then, but in terms of strips. So G prime is an arc labeled with action A, where G is an assignment of values to some of the variables, and A is an action. If xi is vi is on the effects list of action A for some I. So the action's got to achieve one of the elements of G. And we don't want xj is equal to vj prime if xi is equal to vj and they're different. So we don't want to achieve a different value, because then it can't be the last action. And then G prime is the preconditions of A, so A's got to be true, and it's all of the elements of G that were not achieved by A. So we've still got to achieve, so all of these elements here are things we still have to achieve. So A didn't achieve them, but we still have to achieve them before. So the preconditions of A, as well as all of the elements that had to be true beforehand. And as long as the G prime is consistent. That's what we're going to do here. So that might seem like abstract nonsense, but let's look at a particular example here, then it might make sense. So now suppose the goal is we want Sam to not want coffee. If you think about that, the only action that can achieve Sam not wanting coffee is to deliver coffee to Sam. So that's what we're going to have. So the goal is Sam to not want coffee. The action is deliver coffee. And what has to be true immediately before then, right, is in order to deliver coffee, the robot has to be in the office and the robot has to have coffee. Okay, so the robot location has to be the office and the robot has to deliver coffee. And now we have to try and achieve these two. So we don't care about everything else, just only these two are the only things we care about. All right, so how do we achieve Office and Rob has coffee? Well, we can't achieve Rob has coffee at the moment because the only way that we could achieve Rob has coffee is to be in the coffee shop, and we can't be in the coffee shop and the office at the same time. So Rob has coffee cannot be the last action that was used to achieve here. There's only two actions that can achieve this. One is to move clockwise, and that's going to achieve the fact you're in the office and you have to be in the coffee shop. So you can move clockwise from the coffee shop to the office, and moving clockwise keeps Rob has coffee. So Rob has coffee still has to be true before the action of moving clockwise. Or you can move counterclockwise if the robot was in the lab. And in order for the robot to have coffee afterwards, the robot has to have coffee before. So let's look at this node. So to achieve being in the coffee shop and Rob having coffee, well, there are three ways of doing that. We could be in the coffee shop and pick up the coffee, and that would achieve Rob has coffee. Or we could try and achieve being in the coffee shop. So you could move clockwise from the mail room, or can move counterclockwise from the office. Okay, and if we think about this node here, now all we need to do is to get to the coffee shop. Let's look at what this plan says. We need to get to the coffee shop, then we need to pick up coffee, move clockwise, and deliver coffee, and then Sam wants coffee is no longer true. Okay, so that's how regression works. So there's a few interesting things we're going to do in here. Is we can have loop detection and multiple path pruning have an interesting twist. So goal G1 is simpler than goal G2 if G1 is a subset of G2. So it's easier to solve being in the coffee shop than it is to being in the coffee shop when Rob has coffee. And if you have a path to node N, we've already found a path to a simpler goal, we can prune the node to N. Before we could only do it for equal nodes, but now we can do it for simpler goals. And this is more pruning that we can do before now with this. So improving efficiency, we can define a heuristic function that estimates how difficult it is to solve a goal from a state. And if you think about this, is actually the same sort of heuristic function we needed for forward planning. However, you find out that when we play with this and do things, we'll find out that they achieve quite different things about what to actually prune. And we can use domain-specific knowledge to remove impossible goals. So one example is that it's often not obvious from an action description to conclude whether an action can hold multiple items at any time. So the goal might be to hold the coffee and hold the mail. And we don't know, it might be hard to say that that's actually impossible or not possible. So sometimes we're going to use domain-specific knowledge. So if you're comparing forward and regression planners, which is more efficient depends on the branching factor, because they now have different branching factors, because one is going for all the actions that are possible, and the other is talking about all of the actions that actually are useful. How good the heuristics are. And so how good the heuristics are might affect the efficiency of these things. And the main difference is that the forward planning is unconstrained by the goal except as a source of heuristics. So I can only have reachable states and not necessarily states that can get to the goal. So regression planning is unconstrained by the initial state except as a source of heuristics. So it's only using useful actions, not whether the states are possible. Okay, so in class, we're going to have a look at a lot of these again and play and make sure you know what's going on. And we're going to run programs to check them, and that's going to be the next assignment.